In this video, we're going to be looking at some of the quantitative and qualitative relationships between gas parameters. We call these collectively the gas laws. And so we're going to start here with a rather simple one you've probably encountered. It's called Boyle's Law. Now, the concept of Boyle's Law is simple. It says that the pressure and volume of a gas are inversely proportional. There is a little bit of a proviso on this that we do need to be careful about. And that proviso is they are inversely proportional at constant temperature and amount of gas. So if I have a balloon that I'm holding at a constant temperature and I've tied off the balloon so that no gas can go in or out, then Boyle's law definitely applies. Pressure and volume are inversely proportional. If I push on the balloon and try to make the balloon smaller, I'm going to feel a massive increase in the pressure inside pushing out against me. And vice versa. If I stretch that balloon, if I try and make the balloon bigger somehow, the internal pressure inside the balloon is going to be considerably less. Now, mathematically speaking, pay attention to the language here and how it relates to the equation itself. When we see the term inversely proportional, what that's going to mean is that our parameters are going to be multiplied by each other. And so inverse relationships lead to multiplications in our equations. And so the pressure times the volume of a gas at one set of conditions is going to equal to the pressure and the volume multiplied by each other at another set of conditions. Now, the other way that we can look at this is from the standpoint of kinetic molecular theory. And with kinetic molecular theory, again, we had those assumptions that we made. And what we can say with relation to that theory is that if we shrink down the volume of the box, so let's say that our container was this big, but now it's only this big. Well, inside of this bigger container, the gas molecules are moving around, but because there's so much more space, they're not going to collide with the walls of this container nearly as often as they would in this container, which is considerably smaller. Smaller space, more confined area, more collisions are going to occur. More collisions means greater pressure. So that's Boyle's law from kind of a theoretical perspective. Let's take a look at a problem involving Boyle's law. So we're told that we have a balloon filled with carbon dioxide to a pressure of 1.85 atmospheres and a volume of 1.54 liters. If temperature is constant, what is the final volume when the pressure is increased to 2.5 atmospheres? So we can see here we've got one set of conditions. So we're just going to mark that with a 1. And we've got a second set of conditions here where we don't know its final volume. This is a perfect place for Boyle's law because, again, temperature is being held constant. So P1V1 is equal to P2V2. And we can see that my pressure initially was 1.85 atmospheres multiplied by my 1.54 liters of volume. And my second pressure is 2.50 atmospheres times V2, which we're trying to find. So to get this set up properly, I'm going to have to divide both sides by 2.50 atmospheres. That will get the 2.50 to cancel on the left hand or right hand side rather, and atmospheres to cancel on the right hand side, or excuse me, the left hand side. Now I set up and I do my calculation. I got my calculator out here, 1.85 multiply by 1.54 divide by 2.50 to 3 significant figures. I get 1.14 liters. So 1.14 liters is my secondary volume. And that makes sense, right? We have increased the pressure, so we must have seen a decrease in volume. And sure enough, we went from 1.54 to 1.14 liters. So that makes sense. Let's take a look at another gas law, another relationship. This one's called Charles' Law. Now, Charles' Law tells us that the absolute temperature and volume of a gas are directly proportional. And again, there's a proviso here. There's a caveat. At constant pressure, and again, amount of gas also held constant. The other thing that we need to look at here is it's talking about absolute temperature. Absolute temperature means we have to use degrees Kelvin. I can't use Celsius or Fahrenheit here. I have to use Kelvin. Now, these are directly proportional quantities. And again, that should make sense to you. If you think about a hot air balloon, um, you see an expansion of gas because of the heating of that gas. And so that causes the hot air balloon to inflate and to become larger. And that is ultimately what causes the air inside to become more buoyant, and the hot air balloon goes up in the air. So another thing to look at here, we see that we have a direct proportionality here. Direct proportionalities lead to division ratios of variables instead of products of variables. So my volume divided by my temperature at one set of conditions is equal to my volume divided by my temperature at a second set of conditions. And taking this back to kinetic molecular theory, again, it should make sense. We're increasing the temperature of the gas particles are moving faster, they're going to collide more frequently with the container wall, and that's going to cause the walls of the container to expand to account for that extra energy. Let's take a look at this from another concept. So thus far, we've held constant the idea of the amount of gas. What if we no longer did that? To do that, we would have to look at something called Avogadro's Law. Avogadro's Law says that the volume of gas is directly proportional to the amount of gas that is in that container. So what we have there, again, direct proportionality, we see division. Volume divided by moles on each side of the equation. Now, there's a lot of cool things about Avogadro's Law. Avogadro's Law tells us that it doesn't matter what the gas is, the volume of the gas is directly related to the number of moles of gas that are there. And that's a really cool kind of phenomenon. But what we can also look at is if we have similar kinds of conditions, Avogadro's Law sets up for us a really common kind of idea, and that is at a specific temperature and pressure. We call it standard temperature and pressure. STP is 760 millimeters of mercury, 273 Kelvin of temperature, and we can know definitively by this definition, by this law, by this ideal behavior, that 1 mole of gas, any gas, doesn't matter if it's heavy or light, if it's made out of gigantic molecules or small molecules, 1 mole of gas, regardless of type, takes up 22.4 liters of space. That's one of the real beauties of Avogadro's Law. And it's kind of like what we saw with colligative properties in the previous chapter. It doesn't matter what the identity of the gas is, they all fall under this umbrella. Pretty cool. Now, all of these have required assumptions. This particular one required us to have a constant pressure and temperature in order to have this proportionality, which is why STP got brought in here. Other ones have required different things being held constant. What if we didn't have things held constant? What could we do? Well, luckily, we know that all of these things are related to each other. Pressure, volume, temperature, amount of gas, they're all interrelated. And so instead of looking at each one of these individually, what we need to recognize is that each one of them is telling us that if we have things held constant, the product or the ratio of the variables leads to a constant value. And it so happens that these constant values are all kind of the same. And so if I combine these into one equation, I get a constant value as well. And so this particular equation, this one right here, we're going to come back to that one later. This is something that we'll see in another video called the ideal gas law. We're going to focus on this one here at the bottom. This is your combined gas law, or at least was most commonly known as the combined gas law, where we have a fixed amount of gas, but the properties of temperature, volume, and pressure are all capable of changing at the same time. And this is really common because it's kind of difficult at times to hold all three of those parameters constant. But it isn't as uncommon to see all three of them changing at the same time. And we'll show so in this next example. So in this example, I have a sample of oxygen gas at 1/2 of an atmosphere, taking up 10 liters of space at 0 degrees Celsius. What is the pressure of the gas if it is at 15 liters and 25 degrees Celsius? Now, thing that we need to be aware of, obviously we've got one set of conditions here and a second set of conditions here. But before we go jumping into putting those into the combined gas law, we need to take into consideration our 25 degrees Celsius, our 0 degrees Celsius. Those are not absolute temperatures. I need to convert them into absolute temperatures first. So the 0 becomes 273 Kelvin, the 25 becomes 298 Kelvin, and now I have something that I can work with in terms of the combined gas law. P1 times V1 over T1 is equal to P2 times V2 over T2. So plugging in my values now, pressure initially was 1/2 of an atmosphere. Initial volume was 10.0 liters. Initial temperature was 273 Kelvin. And my final pressure, I don't know. My final volume was 15.0 liters. And my final temperature was 298 Kelvin. So working a little bit of algebraic magic here, we're going to have to get P2 by itself, which means we're going to have to multiply each side by a fractional number. So take a minute and try to work that out yourselves. I'm going to come back in here with the full answer in just about 20 seconds. So go ahead and try it for yourself, and let's see where we are in a couple of seconds. So you can see that by multiplying each side by 298K over 15 liters, we cancel out the right-hand side of the equation other than P2. We cancel out the Kelvin and the liters, so all we need to do is to put in the numbers 298 times 0.5 times 10.0 divided by 15.0 divided by 273, and we get a final pressure of 0.364 atmospheres. And so that's where we'll stop for this particular video. In the next video, we'll talk about one final gas law, and that is the ideal gas law, where we aren't looking so much at when things change, but when we need to examine all four parameters at the same time, Until then, have a good day.